2.1, the nature of acid-base equilibria. So Bronsted-Lowry theory is saying that an acid lose hydronium ion and the base will gain in hydronium. Hydronium ion is H+, right? Hydronium ion. Look at that, HCl is losing hydrogen. So this is acid then. And H2O is gaining hydrogen. So this is base. Same thing, NH3 plus H2O give you NH4 and OH. See, NH3 gaining hydrogen, so it's going to be base. H2O, it's losing one hydrogen, so it's going to be acid. Again, Bronsted-Lowry acid, proton donor. Proton means hydrogen because it has a positive charge. And Bronsted-Lowry base is proton acceptor. So we're for the reversible acid. So if you have a two-way reaction, means this is the weak acid base, right? So looking at that, Hc2H3O2 will turn into C2H3O2. It means it's losing proton or hydronium ion. Therefore, it's going to be acid, and H2O is gaining hydronium ion. This is going to be base. So here is conjugate pairs. What is it? Hc2H3O2, it turns to H2H3O2. It's losing hydrogen. So it's going to be conjugate acid pair. And H2O turned to H3O is gaining hydrogen. So it's going to be conjugate base. So as you see, this reaction happening 1.3%. It's a very low percentage of that will go forward. Therefore, this is a weak, as you see, it's losing hydrogen. It's a weak acid. That's why it's going both ways. But that is 99% was going forward, means it's just one-way reaction and it's a strong acid. So weak acid is having both ways. A strong acid is just one-way reaction. Here's HA plus H2O. Again, it will be weak because there is a two-way reaction. Stronger an acid, the weaker is its conjugate base. And conversely, the weaker an acid, the stronger is the conjugate base. Okay, for example, HA plus H2O, H3O plus A. So HA is losing hydrogen, become A. So this is your acid because this is losing hydrogen. If the reverse reaction happening, A will gain hydrogen. So it's going to be base. This is conjugate base, right? So if this is a strong, this will be weak base. If this is weak, it's going to be strong base. So it's just kind of reverse. Same way we can talk about a base. So to practice, please do question number 1 here, page 532. So the autonization of water, here is when two water molecules are reacting, one of them will lose hydrogen and one will gain hydrogen. So H2O gain hydrogen become H3O plus, and this one is lose hydrogen become OH negative. So when you're talking about the K of the water, concentration of the H multiplied by OH is always equal to 10 power negative 14. Thing is coming here, yeah. KW is H multiplied by concentration of the hydrogen, multiplied by concentration of hydroxide, and is always K of W is 10 to the power negative 14. If it is your solution is neutral, the concentration of H and OH are the same, and each of that is 10 power negative 7. So if the concentration both of that is equal, so it's neutral solution, concentration of hydrogen is much more than OH. The solution is acidic, concentration of OH is more, the solution is basic. Again, a strong acid will ionize completely, close to 100%. Monoprotic acid means you're just producing one, it's just losing hydrogen 1 times. Let's just do a question here. 0.15 mole per liter solution of hydrochloric acid is found to have a hydrogen ion, a concentration of 0.15 mole per liter. Calculate the concentration of hydroxide ion. Since I know hydroxide ion, the concentration of the OH multiplied by concentration of the H is 10 to the power of negative 14. If I have concentration of hydrogen ion to be 0.15 mole, means I have concentration of the H plus, right? I have this 0.15 mole per liter. So concentration of the OH then will be 10 power negative 14 divided by 0.15. Which is 6.7, 10 power negative 14. Here is another question. Calculate the hydroxide ion concentration in a 0.25 milliliter HBr solution. So the same way, so it's just going to be 10 power negative 14 divided by 0.25, the same way we did before. You can practice question 4, 5, and 6. This is page 537. Here is strong base. A strong base, again, it will dissociate to its ion 100%. NaOH will be strong. It will give you Na positive and OH negative. Calculate the hydrogen ion concentration is 0.25 mole per liter solution of barium hydroxide strong base. So 0.25 solution of barium hydroxide, see, BaOH2 give you 1 Ba and 2 OH. Therefore, the concentration of OH ion will be twice of BaOH2. That's why concentration of that need to multiply by 2. 2 multiplied by 0.25, right? Therefore, we know the Kw is hydrogen multiplied by OH, which is Kw is 10 power negative 40. You rearrange for hydrogen concentration, Kw divided by concentration of OH. Concentration of OH, we got 0.5, and concentration of hydrogen ion will be this. Same thing, determine the hydrogen ion and hydroxide ion concentration in 500 milliliter of an aqueous solution containing 2.6 gram of dissolved sodium hydroxide. Sodium hydroxide is a strong acid, base. It's completely dissociated into the ion. So 2.6 gram. I need to find concentration of the OH here by turning this one to the mole, turning this one to the liter. So I need to have mole per liter, right? For NaOH, convert that 2.6 gram converted into the mole. So 1 mole is 40 gram. So it's enough that. Concentration of NaOH gonna be mole per volume. Volume is 0.5. Turning the 500 milliliter to liter, so divide by 1,000. So this will give you the concentration of NaOH. Since the coefficient is 1, 1, 1, so concentration of NaOH and OH going to be the same. So we're getting concentration of the OH. Again, Kw is concentration of the hydrogen multiplied by OH. Rearranging for concentration of hydrogen is Kw divided by OH. Concentration of hydrogen, you can easily calculate that. Here, a cleansing solution contains 5 grams of KOH in 2 liters of solution. Calculate the hydrogen. That would be the same thing. KOH is a strong base. You need to convert this one to the mole. Convert, so this is the liter. So finding the concentration of the KOH is this way. And then consider KOH and OH are the same. You use the Kw is the hydrogen concentration multiplied by OH concentration. Arranging for hydrogen concentration. Kw we already know is always 10 power negative 14. OH we got it before, and that would be the concentration of the hydrogen ion. For practice, you can do question number 8, 9, and 10. Hydrogen ion concentration and pH. So pH is negative log of concentration of the hydrogen. Why we use the pH? Because those concentration is huge, right? It's 10 power negative 13. It's not convenient to use that. We use the log to have a better number. So the pH is from 0 to 14. It's scaled from 0 to 14. Closer to 0 is more acidic. Closer to 14 is more basic. Calculate pH of the solution. Concentration of the hydrogen ion is given to you. Just simply, pH is negative log of the hydrogen hydronium. So it's going to be negative log of 4.7 10 power negative 11. Use your calculator. It's 10.33. So it's 10.33. It's very basic. So knowing that pH of the 7 is neutral, pH less than 7 is acidic, pH greater than 7 is basic solution. You know that pH plus pOH is 14. Remember that. pH plus pOH is 14. Convert pH to 10.32 hydronium ion. So concentration of the hydrogen is 10 power negative pH. So that's the formula there. So it's just 10 power negative 10.33, and that would be the concentration of the H. So pOH is negative log OH the same way, and OH is 10 power negative pOH. Calculate pH solution. Hydroxide ion is given 3 10 power negative 6. So just using the formula, put the number there, you will get pOH. Here is the one that I told you, pH plus pOH is 14. What is the pOH if the pH is 6.4? Just, we know pH 6.4, we just rearrange it for pOH, which is 7.6. The pH of the strong acid. Again, the same things. Calculate the pH of the 0.042 mole per liter of HNO3. HNO3 is a strong acid. We have the concentration of HNO3. Basically, because of this 1 mole of HNO3 produce 1 mole of the hydrogen ion. So the concentration of these two are the same. Hydrogen ion is 0.04, the same as concentration of the HNO3. For pH then is negative log of H plus 1.4. Knowing pH plus pOH is 14, rearranging for pOH, you have 12.6. Concentration, if you have pOH, turning to the concentration of OH is 10 power negative pOH, and you will have that. That would be the same process for this question. For practice, you can do question number 12, 13, and 14. pH of a strong base, very similar. Calculate the pH of a 0.02 mole per liter NaOH solution. NaOH is strong, turning into the NaNOH. Knowing the concentration of NaOH will be the same as OH here because it's 1-to-1 ratio. So we have concentration of OH. So POH is negative log of concentration of the OH. We find that POH to be 1.7 and pH plus POH is 14. Knowing the POH, just kind of rearrange for pH, and that would be your pH. The same thing for this, but here you have a 4.3 gram of the BaOH2 in water for 1.5 liter of solution. First, you turn it to the mole, then divided by the 1.5 liter to find the concentration of that. And after finding the concentration, it would be easy to find the concentration of OH. It's just twice of the concentration of the BaOH. And concentration of OH is going to be twice of the BaOH. POH is negative log of the concentration OH. The same way you can use pH plus POH is 14. Using POH, rearranging for pH, give you the pH. Okay, calculate the pH of 0.02 mole per liter of CaOH2. Okay, that would be very similar. For practice, you can do question numbers 17, 18, and 19.